All right. Hello, everyone, and welcome to another special Handmade Hero presentation. Much like yesterday, no programming today. It's actually an interview. And one of the things that I wanted to do at HandmadeCon was get all the people at RAD who work on compression to give us kind of an explanation of how they think about it, and sort of like, for people such as myself who don't know a whole lot about the field, try to get like an expert's point of view on it and sort of like set your mind straight if you want to sort of understand compression things or start getting more into compression. And Charles was the only person at RAD who we didn't get to talk to at HandmadeCon, and he graciously agreed to come on the show for an interview. Hopefully, we'll be able to record this okay with the webcam setup. We're kind of amateur at recording a live interview here, so we'll do the best we can. Charles, thanks so much for joining me.
My pleasure.
I wanted to start out by just kind of asking you sort of the same questions that I asked Fabian and Jeff at HandmadeCon, because I kind of wanted to know your take on it. But before we do you want to maybe give people who don't know you a little bit of background? Because I think a lot of folks probably don't know where the people at RAD came from or how they got there. So.
Great. So I started in software on data compression long ago, probably 20 years ago. And I worked in data compression for a couple of years before I transitioned into the games industry.
How did you get started on compression? Why did you end up doing that as like the first thing?
Just as a hobby, kind of.
Oh.
I started even in like high school when I had started coding. I started playing around with data compression.
Really?
It's the way most people get into data compression, I'd say.
Okay.
It's just kind of out of curiosity and playing in their free time.
All right.
And I found it fascinating, so I started playing with it more and more until it turned into jobs that I started taking on. And I wound up working at Eclipse for Dave Stafford, where we made the Genesis 3D engine. He actually hired me to do data compression there.
Oh, really?
Yeah.
Okay.
Because the idea at Eclipse was to do 3D on the web.
Oh, right. Okay.
So I was doing the like transmission side of that, compressing the content, because at the time a lot of people were still on modems and things like that, and bandwidth was important. So
how long? I mean, I guess I didn't think about that, but we still don't really have 3D on the web today, even as a practical reality. I mean, it sort of exists. So it's been like 15 years or something of
20
people,
years.
20 years of people like maybe sort of going to be doing 3D on the web as a major thing, and it's like, well, not quite.
Right. Yeah.
All right.
At the time, it was kind of too soon in the sense that lots of computers could barely run 3D, and like the web barely worked. So people were more concerned about like, hey, can we just have a web that works, as opposed to let's have 3D on it.
Okay, so you worked at Eclipse, and then somehow you ended up at RAD. Like, what happened in between?
Right. So from Eclipse, I kind of got interested in the 3D engine aspect of it.
Okay.
Started working more and more on the 3D rendering pipeline, and transitioned into doing that as my job.
Got it.
So I moved over to games and worked in games for, 10, 15 years or something like that.
Okay.
Eventually sort of quit games and moved to RAD as, a way of working near the game industry, but not in it.
The periphery, just on that crust.
Yes.
Without having to get too deep into the actual reality of it.
Right.
Okay, so I guess let me ask you the couple of compression questions here that were sort of like the ones that I asked at HandmadeCon. So I'm curious, like, since you've worked on compression for an extremely long time and just have a lot of experience with it, I'm curious, how do you tend to think about compression, like just as a whole, if that makes sense? Like, what do you think about it in terms of it's like, how do you visualize compressors, or like just in terms of your mental space? Sorry if that's a broad question. Well, start there, and then if you're like, I don't really understand what you mean, I'll be more specific. I don't want to pre-bias the answer at all if I can avoid it.
Right. It's a very broad question, and I mean the answer is kind of tricky because compressors can all be very different, or they can look very different in the way that they work. They're always trying to achieve the same goal, but the end result can the way the algorithm works might not look at all like what they're actually doing. So kind of generally the way I think about compressors is I'm always trying to think about the very theoretical aspect of how they're working.
Okay.
In terms of like, what are they actually expressing about the data?
Okay.
Like, what are they trying to model?
Okay.
And then there's kind of the algorithm, or how you express that in the machine code, and that can not necessarily look very much like the theoretical side. But I'm always trying to keep those in mind as I'm working through things.
What do you mean by the theoretical model, or can you give an example of what you mean by that?
Well, so let's talk about compression in general for a second.
Yes.
So the clearest way to think about compression is always in terms of the model coder paradigm.
Okay.
Which is you have an entropy coder on the back end.
Okay.
And you have a model of the data.
Okay.
So the model is trying to predict the data.
Okay.
Normally we work in terms of streaming models, which
Okay.
predict either a byte at a time or a bit at a time or something like that.
Okay.
Though there are more general models.
Okay.
So the model is trying to assign probabilities to your data.
Okay.
Like basically which data it thinks is extremely likely to happen versus
Okay.
which data is rare.
Okay.
And then the entropy coder assigns bit lengths based on those probabilities.
Okay.
Which is just minus log 2p is the correct bit length.
Okay. Okay.
For a given probability.
Can you expand on that a little? Since you brought it up already, do you want to? And you can draw if you want to. I don't know if you want to, but can you expand on that for people who won't immediately know what that means when you say it?
I mean.
Or do you want to pause and put that to later?
Well, I don't want to teach a whole class on data compression.
Fair enough.
Because it's too complicated.
Yeah.
But if you have certain probabilities,
Yes.
you can assign certain code lengths.
Okay.
The code lengths are constrained by decodability. There's something called the Craft inequality,
Okay.
which is a constraint on the code lengths. Like
Okay.
you can't just say every word gets a code length of 0.
Okay.
Hey, you have infinite compression, but it's not decodable.
Okay.
Right.
I see.
So if your input is a bit, it can either be 0 or 1.
Mm-hmm.
You could have a code length of 1 for each of them.
Yes.
That's decodable.
And that's no compression. Essentially, that's a copy.
Right.
Okay.
Yes. That's, both values of the bit are equally likely.
Yes.
Or you can have code lengths that are log 2p and log 2 1 minus p.
Okay.
For any p.
Okay.
That's also decodable.
Okay.
Code lengths below that are going to be non-decodable.
Below what?
Log 2p, log 2 1 minus p for any p. That makes a curve of the two code lengths.
Okay.
And anything that's in that space shorter
Okay.
is non-decodable. Anything longer is wasting bits. It's an inefficient entropy coder.
I'm not sure. I mean, I vaguely understand that, but I'm not sure I totally understand that. So just to be clear, when you're talking about code lengths, right? And in this case, I guess we're talking about potentially fractional bit lengths in this sense.
Yeah. And
so
the optimal entropy coder would be fractional and infinite precision.
Infinite precision, right? So it can
one
be,
of the things you have to deal with is when you go to a practical coder.
Yeah.
Which is obviously not infinite precision.
Right.
It has to bias into this slightly wasteful space.
Right.
And so you want to minimize that bias.
Okay.
How far you go into the wasting code space.
And so I think if I can restate what you were saying about the log p part of things. So what you were saying there was that, like, okay, so if I have fractional bits, I could say that I'm going to assign, 0.2 bits to 0 and 0.2 bits to 1, which would give me this nice compression because now it only takes 0.4 bits per bit. But what you're saying is that can't actually exist because of that theorem, right? We have proven that that's not possible. It still has to sum up to the 1-bit value at the end, right? Is that a fair restatement of what you're saying?
Correct. It doesn't sum up to 1 bit exactly.
Okay.
They don't add up They don't add up to 2 bits.
Okay.
In order to be what happens is when you save on one, you actually gain more on the other. If you look at what log p and log 1 minus p do.
Okay.
So like if you want to save, if you go to half a bit on one,
Yes.
the other one goes to 2 bits.
Oh, okay, right. Sorry. So yeah, I shouldn't say sum up to 1.
Yeah.
Because it's in the log space, it's going to be not that, but
Right.
out of the log space, if it's sum up to 1 might be a way to say it. I don't know. I don't know what the right way to say that
If
is.
you do 2 to each code length,
Yes.
that sums to 2.
Okay. Okay. All right. That all makes sense now. I'm on board. Okay. So back to the original statement of how you think about it. You were saying that you think of it as model and coder. So you basically, which I think does kind of echo, although I don't know that anyone broke it down exactly that way, but that did sound like what people had said in terms of when Fabi and Jeff were talking about it.
Yeah.
So basically, the model part of things is basically saying, I'm trying to figure out what I expect to happen in this stream as I'm seeing it, and the encoder part is saying, well, based on what that front end sort of guess about what I expect to see is, I'm going to assign bits to what it sort of told me I needed to assign. I guess that makes, or if you want to say that.
Yeah, I mean, so the model is, you have some assumptions or some knowledge about the data, and you're trying to reduce the amount of bits that you have to actually send based on that knowledge. Like if I know that you're going to be speaking English to me,
Yeah.
then I know a huge amount about what letters you're going to be using,
Right.
even before you say anything.
Right.
And the way that you express that knowledge precisely in a way that saves bits is through this model coder mechanism.
Got it.
That so what I'm thinking about theoretically is what is the model of the data that I want to create? Like, what do I expect this data to be like, and how do I express that? Or if I have a compressor that is not obviously like a model, like an LZ77 type compressor, or there's a whole lot of other kind of heuristic compressors. They don't obviously appear to be expressed as a model.
Okay.
Some compressors are more obviously expressed this way.
Okay.
Whereas others don't appear to be this way.
And when you say LZ77 as an example of one that isn't expressed this way, you mean because, hey, it's just sort of saying, I refer into the stuff in the stream, but I don't really, beyond that, have a lot of opinion about what I expect to be seeing. I just expect to be seeing things I have seen before. That's about it.
Right. So some compressors like PPM or the PAC context mixing compressors, these compressors are very obviously making probabilities for what they expect the next thing to be, and then coding based on that.
Okay.
So you very clearly see, here's a model and here's a coder.
Got it.
And the way you get more compression is to make the model fit the data better.
Got it.
So that is like one kind of whole realm of data compression where people are just working on making better models. And if you make better models, you get more compression.
And those models are entirely based on the data, so it's like, hey, for every type of data we might be looking at any given time, we have to create models specific to that, because the more specific it is to the data, the better compression we're going to get out of these.
Right. The more you know about the data, the more you can specialize your model to it, and the more compression you will get.
All right. So I guess like one thing I might ask, which is a question that I had, maybe it's a little too early in the stream for it, but since it's already seems to come up. One question that I had as someone who's not a compression expert was the split between prediction and entropy encoding is somewhat, it's not obvious, at least to me, based on not knowing very much, why that is how things split out. Because even from just a cursory understanding of compression, I totally see where you're coming from with that model entropy split, because most things I've ever seen also discuss it that way, right? It's like, oh, here's JPEG, or here's PKZip, or here's any of these things. It's like, that is what they look like. They've got this one part that's designed to sort of like pre-process the stream into these pieces that then get fed into the entropy encoder, and that's what you write out as the stream. But it's not obvious to me why that is, if that makes sense. Like, are there deeper reasons at this point as to why it's natural for that to be the way that things have split out? Is it a historical thing that's the reason that they split out that way, and maybe in the future they won't? Is it just because we're not good enough at compression yet, and later we'll realize that was dumb? Like, can you give some perspective on that as in terms of what the why, as opposed to just the fact that it is, because it definitely does seem to be?
Well, it's just a powerful and useful way to look at the problem.
Okay.
I mean, for one thing, you could consider the alternative, right? Which is there's sort of the theoretical best possible compressor is to enumerate all possible data streams of all possible lengths.
Okay.
And either assign a probability to each one,
okay,
or assign an output code stream,
okay,
to each one.
Okay.
So you're making this huge enumeration of all possible data.
Okay.
Where there's
like every picture we ever want to send.
Exactly.
Is going to be in this somewhere.
Right.
Okay.
So if you think about this, what this data looks like, there's a massive amount of it. 99% of it.
Okay.
Is garbage, like random bits.
Okay.
Which you would never expect to occur.
Okay.
As like an image or
okay,
a text file or something like that.
Okay.
They're
Right.
And then this small part of it is organized data.
Okay.
So it turns out that organized data is, a very small amount of all possible data.
Okay. This sun is getting oppressive.
Yeah,
should I close it out?
Right,
you can keep going. I'll just I'll close the blind so we don't get sun.
So your goal is to assign shorter code lengths to the organized data that you expect to be seeing on a regular basis.
Okay.
And longer code lengths to the random data.
Yes.
So anytime you're doing a data compression, you're always, if you're compressing some data, you're expanding other data.
Yeah.
So it's not like you are just getting stuff for free. You're choosing this data I want to expand, this data I want to shrink.
Got it.
So if you could do this, then theoretically you are working without a specific entropy coder. You can do very fine, since you're on our file system, we only have byte accuracy. You can have byte accuracy lengths of your output, and you can do as good as possible compression without ever getting into anything like arithmetic coding or funny stuff with fractional bits.
And this would basically just be a case of, would you? I mean, so if you actually had this case, so I have, the 17 trillion images that we're ever going to send or whatever, and I go through and I enumerate them all, and I say we want to be able to send all of these. I guess what you're saying is you now just have one number that can represent between 0 and 17 trillion, and you just have that number that tells you which image you had, and that's the entirety of the compressor. Ergo, I don't have to actually have...
Well, and the number would be different lengths for each of the images
based on the probability of the image.
I think is more likely.
So I would still have to get into arithmetic encoding in some sense, wouldn't I? Or
no. At this point, they're just different byte lengths of.
Okay.
Okay. The first couple of bits are the length of the thing.
Right? Okay. All right.
So you can do that without any incremental coding or whatever.
Yeah.
So part of the reason why we don't do that is because we want to be able to process little by little. Right. We don't want to have a giant table of everything.
Right.
We don't have to wait until we see all the data to be able to output anything.
Got it.
So a lot of the work has been about how to do things incrementally, which is where things like arithmetic coding come from.
Okay.
It's just the ability to, what you're trying to do is create a kind of an expression of a multi-symbol probability estimation, but to do it one at a time.
Okay. You mean one at a time, meaning as the symbols come in, you're changing your estimates of their probability? Or what do you mean by one at a time?
Maybe I can draw.
Sure. Go nuts.
This is
should be live.
So what you're trying to do is you have some multi-symbol sequence, and you want to give a code length to it based on the various codes in it. But you don't want to have to deal with lots of things at a time like that. You want to be able to do it incrementally, so you express the probability of the whole sequence as, the probability of 4 characters is the probability of 1 given the previous 3 times the probability of the previous 3. And then you can decompose this in the same way.
Are those in reverse order?
Yeah.
Okay.
I'm doing confusingly reverse order.
Okay, because I was going to say, like...
I'm coding my stream backwards.
You're coding your stream backwards?
Yeah.
All right. Wait, is that because you guys do streams backwards now with RANs? Do you write it all this way? If you hold down the space bar, you can scroll around too if you want to.
I'm just trying to put a probability of D down here in the
All
corner.
right, fair enough.
So, this is just a way of expressing, instead of...
Just make sure that, yeah, it did work.
You may think of word estimation like if you're doing text, the important thing is the probability of the word "the" occurring.
Right.
But you don't want to have to wait. You don't want to have to buffer up lots of things before you run through your model.
Okay.
You want to go one at a time. So you go probability of T first, and then probability of H with T following, and then probability of E with TH preceding.
Got it.
That kind of thing. So the arithmetic coder then allows you to output from each step of the coding and accumulate into a streaming output instead of having to wait until you see the full probability to create the correct code length.
And even if you didn't, you'd still need something like arithmetic encoding, assuming that you wanted those code lengths to be fractional, right? I mean, because you need some strategy for that.
So what I'm trying to get at is that if you buffered up until you got to the end of your file, you don't need fractional code lengths.
Really?
Because you're outputting bytes in the end. You only need fractional code lengths because you're doing a character at a time, and you don't want to be flushing to bytes after each character, because that would be an enormous waste. But when you get to the end of your file, you are flushing to bytes. So if you were just creating code lengths at the end of your file, you don't need fractional lengths.
Okay, so I don't think I understand that then, because, let me just sort of say how I was thinking about it, and you can tell me why this is wrong. So my understanding was that, okay, so if I'm going to output a bunch of stuff, I've got, all these symbols that I want to stuff, and I'm trying to tell you the order these symbols came in. So even if I assume that I already know, like, let's assume that I looked at the entire piece of data, I don't know, maybe it's small, it's 32K or something. So I look at the entire thing, I count up however I choose to partition this into symbols, I partitioned it. I count up the occurrence of all of those symbols, and now I know a specific frequency for each symbol, but that frequency is fractional, right? So it's like, if there were 2,000 symbols and this one appeared like 3 times, it's 3 over 2,000 is the, the frequency, right? So at that point, when I want to go to output these things, I thought that the idea behind the arithmetic compressor was simply that, well, I probably don't want to use, say, 3 bits to represent this symbol. I want to use 3.2 bits to represent this symbol, because that's the closest to the frequency that I could get. Ergo, it doesn't matter if I'm flushing to bytes or not. I still want to pack these things as tightly as possible to make the smallest stream. So I still want something like an arithmetic encoder so that I can always have fractional bits in terms of the length of encoding a particular symbol. Is that an incorrect way of thinking about the problem?
That's true if you're encoding one symbol.
Okay.
But that's what I'm talking about, is the difference between incremental coding versus...
But even if I'm encoding a whole thing, don't I still have to encode the symbols one by one in terms of telling the other side what to produce? No.
No, you don't have, you never have to code things one by one. You have lots of choices.
Okay, so tell me more about that then, just, again, to cement it for people who are not familiar with this sort of stuff or not very good at it.
For example, consider that you have data that only has order 0 correlation, order 0 statistics.
Okay.
By that, what I mean is that you have 2 symbols, 0 and 1.
Okay.
And they have some different probabilities.
Not based on where they are in the stream. It's just always the same probability everywhere.
Right. So order 0 means there's no, it doesn't correspond to whether the previous symbol
Exactly.
is a 0 or a 1 or not. It's just each time you see a new symbol, it has no relation to what you've seen in the past.
Got it.
But there's a different probability of it being 0 or 1.
Got
okay.
it.
So anytime you have data, so first I'll say that one of the goals of data compression sometimes is to transform your data into order 0 data. Because
I see.
if you have order 0 data, then we know how to compress it perfectly.
Right, because now you don't need Markov chains and all these other sorts of things that are trying to look at where we are in the stream and stuff. You're basically saying, hey, if you can transform it into this, it gets much simpler.
Right.
Okay.
So one of the ways of approaching data compression is to try to find a decorrelating transform so that you get into order 0 data.
Got it.
And then we have solutions for it. Okay. So if you're trying to compress order 0 data,
Got it.
if you want to go bit by bit, then you almost certainly want an arithmetic coder or an ANS coder or something like that.
Got it.
It has to be able to do fractional bits because doing integer numbers of bits when you only have 0 and 1 as input is not very useful.
Right. Yes.
But if you don't want to do one at a time,
Okay.
there are lots of solutions.
Okay, so yeah, give me a little, I mean, obviously just a brief thing so I kind of have it in my headspace of like, what's there.
So one of the possibilities is enumerative coding.
Okay.
What you do is you send first you take some block.
Okay.
You send the number of zeros or the number of ones.
Okay.
And then you know that you're just trying to send an arrangement of where those ones or zeros are.
Okay.
Since it's order 0, there's no bias for them to be in any particular place.
Right.
So now this is just a combinatorics problem. It's a choose. There are 3 ones, and I have to put them in 8 buckets.
Right.
There's however many ways you can put them.
And now you just
have to send a selection of that.
Okay.
So you count how many ways there are, and you send it a number.
That is which one of them it is.
From one of those.
I see.
And so you initially chose a block length to do this in.
I see.
As that block length gets larger, you get closer and closer to the entropy. It becomes a perfect coder.
Interesting.
So that is a way.
So in theory, if you wanted to, you could have
coding.
Just done the entire block this way, and then you wouldn't have needed arithmetic, and you have compressed it down to roughly the fractional bit way that the arithmetic would have done it.
Right.
I see. Okay.
Similarly, you can do Huffman coding on, you take 8 or 16 of your bits at a time.
I see.
You do Huffman coding on it.
And you're getting, again, closer, depending how big that block is, you get closer and closer.
You're wasting at most a bit. On average, it's less than half a bit.
I see.
And then as that block gets bigger, you're wasting less.
I see. Okay. Thank you. That was actually very...
There's also optimal ways to do run length coding.
Oh, really?
If one of the probabilities is biased, if one of them is closer to 0,
okay.
So you typically have, lots of 0 bits than a 1 bit.
Okay. So 1 bits are sparse in this file.
So in the case that the 1 bits are sparse, you can code run lengths with, I believe Golem coding is the best way to do it.
Okay. Which is what? Golem coding? Like the little with the ring in Lord of the Rings?
Yes.
Is that what we're talking about here? Or?
I could be wrong about that, but one of the classic...
A precious coder.
Classic variable length integer codes is optimal for run length coding.
Okay.
For bias cases.
Okay.
And again, that's an entropy coder.
Okay.
Though it doesn't necessarily look like an entropy coder.
Okay. Well, so popping back out of that then.
Right.
So back to the question of model versus entropy encoding. So I was kind of saying, was there anything else you want to say about why it tends to break down that way? I guess I'd also be interested in, since you're a pretty theoretical compression kind of person too, I guess I'd be interested to know, Is the
so
does
one of
the
the
theory
reasons-
support that breakdown, or is that breakdown purely practical? Do you know what I'm sort of getting at there? Like, it's like, does the theory suggest that in general coders should be split this way, or is it more just like in practice it turns out to be better to split this way for a number of reasons, that sort of thing?
So I'd say that it's a way of understanding the problem in a clear way,
Yeah.
where you don't get yourself in trouble.
Okay.
Right? Because
Okay.
if you're using a valid entropy coder,
Yeah.
you know you're always making decodable bit streams.
Right.
So you aren't trying to make a perpetual motion machine.
Right,
which
right.
is always a hazard. Right?
Yes.
And it gives you something clear to work on, which is the model. So it's just like, we have an entropy coder which is well understood, and all we have to do is make the model fit the data better.
Okay.
And it's something that you can go and iterate on, and it's just a way of expressing the problem in a way that's easy to understand and analyze, as opposed to the more heuristic data compressors. It's hard to analyze them mathematically.
What are the more heuristic, like, is there an example, if people want to look up a compressor that would fall into the category of harder to analyze, what kind of compressor might that be?
Well, a lot of the classic ones, so like, that's a good question.
Okay.
Most of the ones that are obvious, like LC77, have been analyzed
Enough
in
at this
literature
point. Okay.
that we understand them as models now.
Okay.
They didn't appear originally to be models.
Okay.
But now we know they are.
Okay.
Things like block sorting. There are difficulties in how we understand these as models.
I see.
In a practical sense.
And I guess, would I be correct in saying it sounds like, I mean, just from hearing about it, or for the limited amount that I know about it, it seems to be sort of that entropy encoding seems to be much better solved in terms of like, hey, we can give you a particular definition of a problem, and then we can give you an entropy coder that like exactly solves that problem. Whereas data modeling feels a little bit less like that so far. Like it feels like it's a little more Wild Westy in the sense that, I guess, is part of the reason you break that up is because, hey, entropy coding is very well solved for certain specified problems, so you can just take that part out of your equation and be focusing on the part that's maybe less solved. Is that a reasonable way to phrase it, or is that not really true?
Yeah.
Okay.
That's a good way to phrase it. I mean,
Okay.
So entropy coding, we thought that we knew all the entropy coders until ANS appeared out of nowhere.
Why don't you,
That's
since
interesting.
you guys did some of the pioneering work on this in terms of shipping ANS encoders, talk a little bit about that, because that was an interesting inflection point, I suppose. For people who don't know about ANS encoders, who aren't familiar with that, could you give a little background on like what happened there? Because this was an odd story in some sense.
Yeah, very, very odd story.
Yeah.
So this guy, Jarek Duda,
Okay.
some years ago, 4 or 5 years ago,
Okay.
wrote a paper about asymmetric numeral systems and like lattice encoding.
Okay.
And so a lot of people noticed it.
Okay.
Like I noticed it and commented, "Hey, this looks interesting."
How did you find this paper? You were like, I mean, because like not very many people
Right.
necessarily knew about it
I
at the
must
time.
have, I don't recall, but I
Okay.
must have seen it on someone else's blog or something.
It was
that,
like, hey, I noticed
hey,
this
there's
thing.
this
Okay.
new thing. It looks
Okay.
weird.
Okay.
Nobody really understood it. I didn't understand it.
Okay.
Because it's the original paper was written in a very abstract, mathematical, obtuse way.
Okay.
Nobody really saw how the practical implementation of that would look.
Okay, so people kind of read the paper and were like, all right, that looks kind of interesting, not sure I get why or how we would
Right.
use it, but hey.
So let me back up a tiny bit.
Sure.
On entropy coding, like with arithmetic coding, it's very easy to understand how to to write a bad arithmetic code or one that doesn't work very, like,
Okay.
that the implementation is terrible, that
Okay.
it's slow, or the most obvious way to write it requires buffering up the entire data with infinite precision or arithmetic.
Right.
So
Yes.
the tricky bit about arithmetic coders is how do you translate it into an implementation? How do you make it incremental? You know, how does it work with finite precision? And that kind of step is a little bit, it's not, there's not a formula necessarily for how to make your arithmetic coder.
Okay.
There have been many over the years. There are a lot of different
Yes.
ways to do it.
Yes.
And there continue to be innovations in that.
Okay.
As we have found slightly different ways of expressing the operation. So ANS originally looked like a new way of expressing the algorithmic operation of entropy coding.
Okay.
Which, if that's all it was, it's not very interesting in the sense that.
Okay, so basically, like, at first it was kind of like, oh, hey, someone did some theoretical work here, but it's not immediately clear that this would change how we would actually type code into a computer.
Or it, you know, it was a different mathematical way of expressing entropy coding, but it wasn't obvious that if we typed that into a computer, it would be efficient at all,
Right.
which is what we're interested in, right?
Got it.
We already have entropy coders that get us as close to the entropy as we want, so
Right.
that is not the issue.
Right.
It's just a question of how efficient can it be, and the
Right.
problem being that efficient arithmetic coders are difficult.
Yes.
There's issues.
Right, Huffman is much faster than arithmetic in those days, right? Like, meaning you typically had a significant speed difference. I remember, especially at some point, there was sort of like, oh, it was kind of a divide per symbol, or then there were like kind of table-driven methods for arithmetic or whatever, but they were much more complicated than the Huffman kind, which could just go direct and be very fast, apparently.
Right.
I mean, this is, again, very cursory knowledge in my head, but I just remember this at RAD at the time when I was there. That seemed to be kind of the case. So
Yeah. And so, like, doing fast arithmetic coding is a whole huge
Thing.
field.
Yeah.
There's tons of approaches.
Got
There's
it.
table-based approaches. You can go binary, and
Yeah.
so, but they all have drawbacks. You know, it's not like. So the interesting thing about ANS was, you know, some years later, Jan Colette started looking into implementing his own. I believe that he kind of had the idea on his own.
Okay.
It turned out to be an ANS implementation.
Oh, really?
And the implementation was interesting.
He was not aware of ANS at the time?
We'd have to ask him about
Okay,
his
so nobody
history.
knows. All right.
But my understanding is that he was fooling around with ideas on his own. He had some problems with his ideas and read the ANS paper and realized
That it was the same basic idea or something?
that like this paper solves his problems, that it's the same idea and it
I see.
has the answer.
Okay.
So his implementation of ANS showed that it was quite interesting.
Okay.
And then we started looking into it and we're like, yeah, this actually is very interesting.
Okay.
Because when you express ANS in terms of machine operations, they turn out to be quite appealing.
I see. Okay. And this is just an artifact of how the ANS math works out, is that when it maps onto actual instructions, it maps on better
Yeah.
than arithmetic.
Right. It's actually,
Okay.
it's very similar to arithmetic coding.
Okay.
There's it's something I touch on in my blog a tiny bit.
Okay.
I didn't really go into it in a great way, but ANS is very similar to the backwards arithmetic coders, which
Okay.
was the original way of doing arithmetic coding.
Okay.
It's why ANS streams are processed backwards.
Got it.
They're-
And why you wrote on the blackboard backwards, potentially?
My randomness.
Yeah.
So ANS is a LIFO coder.
Got it.
And the way it's building up the probability in this way for a multi-symbol sequence, and the way it flushes out incrementally in order to stay in finite precision.
Yeah.
Is kind of backwards from the way arithmetic coders do it.
Okay.
It flushes out the bottom bits instead of the top bits.
Okay.
And that kind of winds up being the magic of what makes it so interesting.
Really?
Yeah.
Okay, so the fact that it flushes out bits from the other side of the value turns out to be that important in authoring the compressor that you can get, oh, well, I guess I should say decompressor, since that's usually what you care about, I suppose, is decompression speed, at least for RAD style stuff.
Yeah.
That one aspect of it turns out to be that important. Interesting.
Mm-hmm.
Why? Is there a way you can explain why without too much detail, or is it really like, no, you got to understand the whole thing? Or is there sort of a like vague why you can give? Because at first blush, you wouldn't think, right? If you just asked someone like, oh, hey, yeah, you know, you had this thing and it was flushing out bottom bits before and now it's flushing out top bits. I don't know that they would immediately go like, oh, that's clearly going to give me so many more options than I had before, right? And maybe that's...
the key thing is that it allows you to know your renormalization interval. So the way we talk about doing this is renormalization. And in arithmetic coding, because it's FIFO and you're sort of zooming in as you go, that zoom factor is a variable.
Okay.
Which is what leads to you having to do a divide.
Okay.
Whereas with ANS, you're building up from the back.
Okay.
And you're dropping bits out of the bottom.
Okay. Which
allows you to get to a fixed kind of code word size and stay there. Which means that you don't have to do the divide.
Interesting. Okay. So in arithmetic, the window is narrowing over time, and in RANDs, it isn't. The intervals.
Yeah. One way to think about RANDs is that you're building up a large integer.
Okay.
And the entropy coding comes from the fact that if the integer is shorter, you send fewer bits.
Okay.
So you're building up this integer x.
Okay.
And you wind up sending log 2 of x bits.
Okay.
That's what RANDs does.
Okay.
So in RANDs, the more probable symbols make x grow less, and the less probable symbols make it grow more.
I see.
So, as you're adding more probable symbols, your integer is growing small amounts.
I see.
Whenever you add a less probable symbol, it takes a bigger step.
Got it.
So, if you didn't do any streaming out, you would just be building up this large integer. You get to the end, you see it's log 2x bits, and you send it.
Got it.
And that is an ANS coder with no flushing.
Okay.
What the practical streaming ones do is build x up to 32 bits or something, and then flush out bottom bits as
8
they
or
go.
16 or something like this, and then start adding more bits in.
Yeah.
I see, and this is probably too detailed to ask, but I'm just going to ask it anyway, then you can just say, like, ignore it for now. If you're building up an integer, you're actually building it up in bit order, though, so meaning you're not incrementing the integer, this giant integer, you're not really incrementing it. You're actually concatenating bits onto it, meaning you know the low order bits of the integer right away.
No.
Then how are you flushing? Does that make sense? Is that a dumb question?
No.
Okay. All right.
So that is the key to the ANS streaming.
Okay.
So when you do streaming ANS, you don't make the same final number that you would if you didn't stream.
Okay.
And the only reason it works is because, so you're right. You are actually like multiplying this integer up and adding to it.
That's what it sounded like you were saying,
those
but
bottom bits should
change all the time.
They should keep changing.
Exactly.
They never
That's
stop
what I was
changing, right?
sort of asking.
But the way the streaming scheme works in ANS is when you hit the streaming threshold, you just output them anyway.
Because you assume, look, the decompressor doesn't need the bits of the final integer. It just needs the bits of where I was at this point in the final integer.
Right.
So as long as I give it that, it knows where it was, and it's just going to do the same thing to get to that final integer that I was doing. That kind of a thing?
Exactly.
Okay.
So that is the key of
Got
ANS
it.
streaming, is that the encoder and decoder have to be in lockstep in that
Okay.
sense, that they have to stream in the exact same spot.
Okay.
And that's actually something that there's some careful analysis that has to be done to make sure that the encoder and decoder,
Can do so.
well, they have to, right, they have to have enough information to know to do
I
so
see.
in the same place.
I see.
Without sending more bits. You don't want to send another bit that says like,
Hey,
hey, do your
thing
renormalization now.
I see.
So you have to ensure that you can tell from the code word value itself
I see.
when to do that,
Got it.
and that the decoder will be able to replicate what the encoder
What the encoder did.
Exactly.
And
That turns out to be a specific condition, which is interesting. That's
part of the theory of learning ANS is exactly how that ends up being chosen or done
right. It becomes a constraint actually on
on the way you do it.
the way you build your code word table.
So one other, I guess, question while we're on that subject, because that was actually
So that's
interesting. But
kind of an
yeah.
interesting difference between ANS and arithmetic is that with most arithmetic schemes, what you're trying to do is approximate this imaginary infinite precision thing that you would get, if you did arithmetic coding on the whole file and never flushed it out.
Yes.
Eventually you would get some fractional thing and
Yes.
you would output that
Got it.
perfectly.
Yes.
And the streaming methods are just trying to approximate that.
Got it.
And they generally don't put a constraint on how the decoder does its streaming.
Okay.
That the decoder could stream in bytes or bits,
So
or
it doesn't matter.
could do it at any time.
Got it.
So that's a big difference to ANS, which turns out to make a big difference in how you can implement it.
And if I could ask one more question, I guess there, just a sort of perspective question. What is because I assume that it's related to all of that, if it's not too hard to give a little bit of insight into, because I've actually seen ANS compressor before, why does the encoder and the decoder run opposite each other in direction? Meaning, in an ANS coder, unlike when I've seen arithmetic, typically the way that they're implemented these days is you put like you said, it's FIFO both ways. It's like I put in a bit stream into the encoder, it outputs that bit stream in order, just smaller, and then in the decoder, in comes the same bit stream, and it comes out in order, now decompressed. But ANS goes the other way around. I take a bit stream, and if I put it in order and then decompressed it, I'd get the flipped version of it. And so when I see ANS encoders, they typically have the encoder run backwards through the stream so that when the decoder decodes it, it comes out in the correct order. Where does that flipping come from? Is there an easy way to sort of think about how that is happening, or does that require understanding ANS really deeply to have any idea why?
It comes from this streaming mechanism.
If you use if you hold down the space bar, you can just drag and pan around.
So if I'm trying to send my ABCD stream, the way ANS works is you get your first symbol, and this goes into your accumulator.
Okay.
Then I get my next symbol, and X does something is scaled up, and then I add on something.
Okay.
And then let's say it's time to flush out.
Okay.
So I drop some bits out of X.
Okay.
They go out to the stream. I'll build my stream down here. Now X is reduced. And when that has happened, my new X has lost information about C and D.
Okay.
I can no longer decode C and D.
Okay.
So then I put B in, and I do the same thing. It scales up and adds something in. And maybe I stream out again. And now I can't decode B anymore. And then I put A in to X. I scale it up and add something. At this point, from my X, I can only decode A. Therefore, I have to go backwards of how the decoder went.
Okay.
because I've streamed out the information from the end of the file already. You know, in my file are the low bits of X that I had before. So, whoa.
Sorry. You can
My
control
column
C
is
that.
down.
There you go.
So if I'm going to decode, to decode, so I put the final value of X in my stream. So to decode, I need to take from the stream, and I can output A, because that information was the only thing that was in the final value of X. And then I need to input some more bits. So after I decode A, my X changes, and I'm going backwards. Now I need to stream in my X changes again. Now I have enough information to output B. And I go backwards and I stream in again, and now I have enough information to output C and D.
Well, I guess looking at that diagram, it certainly makes sense, but I guess I might turn the question around and go, shouldn't that have been the case for all entropy encoders that were arithmetic-like? Because with an arithmetic encoder, I would have thought the same would be true. I'm putting these symbols in, and presumably when I flush, I'm going to lose information about
Right.
the earliest symbol that I encoded. Like, why are they different in that regard?
Well, that's what I was trying to hint at in terms of flushing from the top,
Top or the bottom. And it's that difference which bits get flushed.
Right.
I see. So if your entropy encoder flushes bits from the top, it can be in order both directions. But if it flushes from the bottom, it's going to have to run reverse.
So
Would that be a fair statement?
Yeah, we'll
Okay.
just do a classic arithmetic coder real quick so you see the difference. So a classic way of thinking about arithmetic coders is you have your number stream. It's so hard to write on this thing.
Sorry.
Between 0 and 1. I'm not used to it.
You can hold it like a pen. Just you can yeah.
Yeah. So you have your thing between 0 and 1. You have probability intervals for, let's do binary. So you have a symbol 0 and a symbol 1 with different probability intervals. As you code each one, you shrink your full range to that interval. So you started from 0 to 1, and you shrink to this range.
Okay.
So we shrink to that range, and then now we're subdividing within here as if this was 0 to 1. This
Okay.
is the renormalization step.
I see.
So then we say we code a 0 bit, now we're shrinking to this range, and you keep going. And this gets smaller and smaller, which is
I
why
see.
you need infinite precision.
Gotcha.
And eventually, if you could do all your bits in your file, you wind up with an infinite precision number, somewhere out here.
Gotcha.
That is, very finely specified.
Gotcha. And this is sort of the anecdotal version is the like, hey, you can encode all the data in the world on like a metal bar just by picking the right distance along the metal bar and making a mark like precisely there. As long as you didn't need more than molecular precision, you could encode,
Right.
the Library of Congress or something.
Sure.
This is that process.
Yeah, right.
Okay.
You're subdividing ranges.
Yeah.
So in order to specify this final number, if you didn't know the length of the file, you would have to specify it with infinite precision.
Okay.
Okay.
Gotcha.
Which obviously you don't want to do.
Right.
Since you do know the file, you know the length of the file, you know where the closest possible
two sides of, the bracket of anywhere in between here and here would give me this file because everything else is past the end of the file.
Right.
Got it.
Exactly. So you know the two closest neighbors, so you only have to specify enough bits of precision to differentiate your final stream from
To that level of detail.
Right.
Got it.
So
Okay.
that winds up giving you the length of your code stream.
Got it.
And the way to do this incrementally streaming is as soon as let's see, my mid area, my 0.5 is here. My initial probabilities were not in the middle. So as soon as your coded word goes to either, your whole interval has to go to either side of this bit, then you know that, so let's call it this point, my high goes, or my low goes over 0.5. I know that my first bit in this final sequence will be a 1. That means I can output a 1 bit immediately,
Okay.
and it will never change, no matter what I code in the future.
Okay. All right.
So now
I see.
I've output my 1 bit, and then I can renormalize onto this interval and grow this up to 0, 1.
I get it now.
And you do that over and over, so at this point I could also output a 0 and another 0 and a few times actually.
Okay. I see.
You're
Because
actually outputting the same bits as you would for infinite precision, but you can do them
yes,
from the top
down.
once you know that you will be within that interval.
Got it.
And we're ignoring the middle underflow zone for this discussion.
Okay, yeah.
Which
Yeah,
is
yeah.
one of the practical issues that you have to deal with.
Okay, so let me ask one more question on that. Is this too many questions? How are you doing? Sorry.
No, we're good.
Okay, good. Let me ask one more question there, because something interesting that I kind of wanted to ask about along those lines. So, because based on what we talked about before with the ANS encoder, like you were saying, it's not necessary to actually output the bits of the number that we're actually building. So that large integer that is the integer that's actually how we're encoding the stream theoretically is not what we actually output. That number is being built, but the thing we output is actually an intermediate, a portion of the intermediate value that we were using to construct that number. So it's like a step in the summation up to that number, or multiplication up to whatever the ANS fundamental equation is, or whatever. Why do I have to flush out of the bottom then? Because if all I'm trying to do is tell the decoder a clue about what the state was, what makes the low bits of my interim solution so much more interesting to flush than the high bits? Is that too minutiae to go into, or is there an easy way to sort of mention why that turns out to be the important part?
There's an easy way to
Okay.
talk about that. So your goal with ANS is to get the growth of your number x correctly.
Okay.
So because the size of x is, what gives you log 2 of x,
Right.
gives you the length of your stream.
Which is what we wanted.
So your goal of your entropy coder is to make that length be what it should be theoretically.
Right.
It should match the probability model
Okay.
to be as close to an optimal entropy coder as possible.
Got it.
So the goal with ANS is to make the growth of x as close to that as possible.
Right, and the growth of x in this case means for the symbol table, every symbol was supposed to be assigned a very specific way in which x would grow, and we want to be as close as possible to that growth in order to hit our target. Any error in that growth and our encoder gets worse.
Right.
Yeah.
So when you stream out of x,
Mm-hmm.
you're making the final value of x slightly wrong.
Okay.
You want to do that in a way that minimizes the damage to how x grows.
And of course, the lower bits are the least relevant.
Right. Exactly.
Got it.
And so that turns out to be a factor in how precise your coder is.
Got it.
So, for speed, frequently we want to do byte-wise renormalization or byte-wise streaming, which means we're putting out 8 bits at a time.
Got it.
And the more bits you stream out of there, the more you are screwing up the value of x, basically.
Got it.
And in some cases, we've even looked at doing word at a time output, which increases an even bigger cost.
16 bits at a time.
Right.
I believe Fabian posted a reference implementation of ANS that was 16 bits at a
Yeah.
time, in fact. That obviously was not trying to be optimal in any way, speed or space, but it was just kind of like, here's what you do it. I think his was 16, if I remember correctly.
Yeah, he did a 16 at a time one.
Yeah.
And because you know your value of x at that point is bigger than 2 to the 24, you can define your interval in different ways.
Yeah.
But typically we choose it to be between, x is between 2 to the 24 and 2 to the 32.
Okay.
And then you output 8 at the bottom. Whether it's got +0 or +255 added on 2 to the 24, turns out it's not a very large amount of the value.
Got it.
So it doesn't cost you very much in terms of your coding efficiency.
Got it. Whereas if you streamed out the high bits, you're essentially destroying the most important part of the data at that time, so it would be like an awful encoder at this point.
Right.
That's very interesting. Okay. All right, so was there anything else you want to say about that before I ask a sort of a separate stream of questions here? That all seem pretty good to me from in my head, but
Yeah, that's good.
I have a question about sort of one of the things that was underlying a lot of the stuff we talked about that I don't think I really know necessarily why. I was going to ask about that. So in my experience when I've used compression, and this is more of as a user of compression, not as somebody who actually knows anything about it and is like implementing it, incremental is rarely something I actually care about in any practical sense. Meaning, you know, from the perspective of, say, a game like the game I'm working on now, the way that the assets system is structured is everything's broken up into streamable chunks that I'm only loading to manage paging and stuff like that anyway. So both the encoder and the decoder always know they're working with some fairly small 256K at a time pieces or something like this. So why is incremental so important? Is it more about getting compression localized, or is it like, why do we even care about, like a lot of things you're saying like incremental, why aren't compressors generally written just to assume that they get to see the whole stream and work from there? Am I missing something about that, or did you have something you want to say about that? Because that, in my perspective, while I can understand why certain live, like, you know, this streaming that we're doing here, maybe you might think of it as a long stream and you need to be incremental or whatever else, but in practice for games, streaming in that sense is almost never necessary, and the usage of the encoder and the decoder could always have all the data if they wanted to. It's really just not that big for the sizes that we tend to care about. Can you talk a little bit about that, just to maybe put it in perspective?
Yeah, there's a lot of issues there. So one thing is, for entropy coders, the reason that we look at incremental is partly because of the finite precision issue.
Okay.
That you have 32-bit words or whatever to work in. You can't do that many symbols in there.
Got it.
With precision, so you have to do one at a time. So you have to have a streaming way of doing that.
So mostly that's to keep the computation time down, because if you kept allowing it to grow and grow, you would have to do like a big num sort of thing where we're doing multiplication on, you know, 4096-bit integers and beyond and
Right.
stuff.
Yeah.
Okay.
In terms of compressors in general, I would say historically people were very interested in incremental because they actually did incremental compressors.
Okay.
Like back in the Shannon Bell Labs days.
Right, okay.
People actually wanted to be able to flush 1 byte at a time
right.
over a very slow channel.
Right, because they just had much more severe practical constraints than we do now, or
Right.
whatever.
I mean, if you're doing a telegraph,
Yes.
you actually
Yes.
you don't want to have to buffer up 1,000 symbols before you get anything.
Got it. Yeah.
That's much less of a concern now.
Yes.
Like almost everybody is working on at least some kind of packet.
Yeah.
So there are, I would say that people have moved towards looking into blockwise compressors that
Got it.
don't work incrementally.
Got it.
There are things like hierarchical grammars and block sorting and things like that that fundamentally are whole file only.
Okay, so they start out with the assumptions like, look, we're just assuming we get to see everything, and the point of this compressor is to look at all the data first and make some decisions.
Yeah.
Okay.
Most compressors are still incremental. Partly it's a practicality issue that, I mean, so there's a lot of factors there. Like, even if you could do whole file compression, you usually don't want to, because you want adaptability. You want your compressor to be able to change as it goes through.
Yes.
So even if you had a whole file compressor, let's
Yes.
imagine for the moment,
Yes.
say you have a block sorter or something like that.
Okay.
In order for that to be optimal, you would want to find regions of the file cut
Right.
that give you better compression by not doing whole file,
Yes.
because real data is very changeable. You don't want to just make a model for a whole file and apply it across the whole file.
Right.
So by doing a streaming compressor, even if you don't care necessarily about the streaming capability of it, it allows you to make it learn over time and not forget over time is important.
Right. So basically, like in some sense, the streaming is a relatively efficient way to have localized statistics for your statistical model. It's like it's sort of only looking at a narrow section of the file, and since we assume that typically things in the file tend to appear close together if they're similar or something like this, in circumstances where that's true, this will do well, because it won't be trying to use statistics from very early in the file to compress things late in the file when they are no longer applicable or things like this.
Right.
I see.
It's also a good way to limit memory use. If you only have 4 megabytes to put your model in,
Gotcha.
you don't want to make a 4 megabyte memory for the model of the whole file, because that is not very much precision for the whole file.
Got it.
You'd rather have a 4 megabyte model of a small region and scan that over so that you actually have kind of more bytes of model memory per byte that you're trying to work on.
Got it. All right, 2 more things I wanted to ask, if that's cool. So I wanted to ask a question from the theoretical perspective and kind of touched on this.
So, let me go back to that.
Please do.
So the modern Noodle compressors are not streaming. Kraken and Mermaid and so on.
Oh, really?
Yeah.
Okay. Do you want to talk a little bit about that? I didn't know that. So they are block-based in a sense. You give them, you're like, here's the chunk.
Yeah.
Go nuts.
Yeah, they work on blocks.
Okay.
And part of that is just taking advantage of the efficiency of not having to be streaming, that you can kind of work on chunks at a time.
Yeah.
Instead of having to necessarily do one by one output.
Okay. And that is for what purpose? Is that to achieve better compression, or is that for better efficiency? Like, what was the?
That's
or is
for
it both?
speed.
It's for speed.
Yeah.
Okay. Because that way you can know, hey, this is how much I'm working on, and I can look at it and make decisions about what would be the fastest way for the compressor to operate here, or something like that, or?
It's about being able to reorganize how the output loop works, basically.
Okay. The output loop meaning just the decompressors?
Yeah.
Okay.
So, I mean, the simplest way to think about it would be like, say you're outputting, you're trying to output some data, and you have a bit that tells you whether to output an A or a B.
Yes.
If you're going streaming, you have to go through each byte of your output and check that bit and go, okay, either I output an A or a B.
Got it.
So instead, we're trying to reorganize so that we can do like, let's output a bunch of A's ahead, and then we output a bunch of B's ahead.
Okay. Okay. I think I see what you're saying here. So basically, you're saying it doesn't even necessarily write in order. So meaning it may go write an A 6 bytes away, and then write a B in between?
Yeah, look.
Is that a correct statement of what you just said? That's what I thought you just said, but I wasn't sure.
I'm not going to go into the details very much. So
Okay. All right.
We should probably move on, but
Right.
I'm just mentioning that.
Fair enough. Okay, so ignoring proprietary high-tech compression. Let me ask the other question because they did not involve anything OODle specific.
Yeah.
So I, sort of along the lines of what I asked earlier, and this is, again, sort of more my curiosity about the subject matter from not having ever had the time to sit down and really understand it myself. I had like a bunch of questions like, this is what I would look into if I had time to like try to build up this knowledge. And so I'm trying to cheat by asking you these questions.
Yep.
So when you look at something like an arithmetic encoder, or maybe a Huffman encoder, and you look at something like LZ. So one of the interesting things about these from the cursory inspection is like an LZ encoder is a fairly old encoder, right? I mean, it's like 40 years old at this point, roughly, right? LZ77 was 1977 or something, and it's like 2016, 2017 now, right? I guess so. We're literally like 40 years away from the invention of this thing. Yet the typical compressors that are used to compress generic data are still these kinds of compressors, like LZNA, which is the most commonly used high compression variant that I know of. LZMA, sorry. LZNA is yours, I guess. So LZMA is still using variants on those algorithms, from what I understand.
Sure.
Right? So I kind of have like a two-part question there. The first question is there some specific reason why we haven't moved past those compressors? Are they at a sweet spot in terms of being able to compress generic data that is simply impossible to get by in any practical sense? Meaning, like, in order to like make significant improvements on them, you're going to end up in a position where you're doing an incredibly large amount of work to get very little practical return. Like, did they hit a curve particularly well? Or is it more the case of like, we just don't know yet, we haven't been able to make theoretical improvements here, that sort of thing? That's my first kind of question about those, Huffman arithmetic LZ, which seem to kind of be in this like, we still use them today, they're still the best, whatever, in terms of like, so that's the first question. And I have a second question, which I'll wait till after for, but that's kind of the first one, my second one's related.
I mean, the answer is just that they're good algorithms, right?
Okay.
I mean, we still use good algorithms of all kinds,
Yeah.
right? We still use A-star and whatever, we still use quicksort.
Okay.
Like, when there's a good algorithm that happens to be kind of a sweet spot of implementation, you're going to keep using it.
Okay.
And you modify it slightly over time.
Okay.
But you don't go to something else unless there's a major discovery, which there could be.
Okay.
I mean, inventing new data compression algorithms is not like a science that you go and chip away at and they just get better, right? It's like you can always get more compression by throwing more work at it, by making the model better, by refining. There's, you look at anything like LZMA, there are every single spot where it does coding, you say, I could compress this better.
Okay.
But it would take more CPU work.
I see.
Or more memory or something. So then it's a question of, is it worth it to throw that at that? And
the answer in that case is almost always no, I guess. So it doesn't.
It depends what trade-off you want, what your goal is. But there's no like magic. So what happens with data compression is there's kind of obvious vectors to work on things. There's like you can take any existing algorithm and throw other existing algorithms on it. They compose very easily.
Okay.
So you can toss ppm into LZ.
Okay.
Or, you can take something that does Huffman coding and replace it with arithmetic coding, right?
Okay.
So you can always modify these algorithms. You're not really inventing anything new.
But you're kind of bolting together a new machine out of the parts.
And you can trade off your speed versus compression ratio that way.
Gotcha.
But you aren't making a big step into, unexplored territory of efficiency.
Got it.
So, like, is there a big step that would give us more compression at
most of the time,
high speed? We don't know.
Okay.
Like, we haven't found it yet.
Okay.
Maybe there is. Maybe there isn't.
All right.
I mean, it feels like there isn't. There's nothing obvious.
Because we should have seen it by now if it was. Okay, yeah.
But maybe, that's like with ANS came out of nowhere, and block sorting came out of nowhere. When these things do appear, they tend to be like, wow.
Unexpected.
Right.
Okay.
It's because if it was something expected, somebody
would have
have
had it
seen
in 40 years
already, right?
Okay.
Because people are looking at this all the time.
Got it.
It tends to be something weird that comes out of nowhere, and you're like, oh wow. So maybe it doesn't seem like there's that much
fat left in it.
I mean, if you think about what you can express in terms of machine instructions that makes a data compressor, it's hard to imagine where it is.
Okay.
But who knows,
Yeah.
And the other factor is that as the hardware changes, the algorithms that work well on the hardware
can change as well.
Right. So the things that we're doing now are different design choices than we would that we were making 20 years ago, just because the hardware is different.
I suppose it's also true that in general the trade-offs are constantly changing in terms of what you even want in terms of compression, because nowadays there's a whole suite of things that you might not even care about. I mean, it used to be that compressing your CD collection to MP3 was like a really important thing that allowed you to have that CD collection digitized at all. Nowadays, you really just don't care about 10x smaller CDs for your, like, whatever. Like, I can store the whole thing uncompressed and don't care.
Right.
So it's definitely true that, like, what you're, nowadays bandwidth is probably the more important thing that people are trying to compress for, or things like this, and so you're looking at, more of those use cases. So I suppose, like, what you actually want your compression to do and why probably moves as well, which could change
Totally.
what the relevant thing is, right?
Yep. The big thing that's happening, I mean, there's a lot of, obviously, like 4K video and things like that is a huge issue for compression.
Yes.
The other big thing is the speed of disks with like NVRAM disks and things
Yes,
like that.
right.
Has like massively changed. So
Yes.
the idea of like using compression to speed up I/O has changed dramatically because of that.
Except on consoles still. Right. So yeah, someday we won't care about that anymore.
Right.
Because we're not quite there yet. Okay, so last question that I had. This is kind of a bit of a minutia question, but it's still one of those ones that I feel like I'm just curious about in the, like, I just don't have enough theoretical understanding of a lot of the stuff to answer it myself. So from a layman's perspective, when you look at something like LZ Huffman or something like this, or LZ arithmetic, as a way that people implement a compressor, one of the things that's kind of confusing about why it works the way it does is that it sort of seems like, for lack of a better term, there's an arbitrary decision about what is a symbol versus what is not a symbol. And what I mean by that is, if you take a look at like literature or something like that talks about, say, arithmetic encoding, it makes very simple, understandable sense when you read it. It's like, let's suppose we have this alphabet of things we're trying to encode. We don't care what they are. You can make up whatever you want. You can say how many symbols you want and what they are, and all we really care about is that you can assign a probability to each one, and then that probability is accurate. And then we make this arithmetic encoder, and off you go. That's a pretty easy thing to understand. When you extend the system out to something like an LZ encoder with an arithmetic backend, all of a sudden there's this sort of idea that, like, well, okay, so what a symbol is in this case is the output of the things that the LZ compressor cares about, which means, we've got symbols of the form, say, there's a look-back distance. I need some way of expressing that, so symbols could be offsets of things. I've got another thing, which is symbols, which are, I have to encode literals, so in some sense I have symbols that would be the actual symbols I would have talked about if I just had the arithmetic encoder. Those are still involved there, and so on, right? And what's a little bit difficult, and this is my question, what's a little bit difficult to wrap one's head around, I feel like, is it seems like these sorts of things are treating that very fast and loose in some sense. It's not obvious to me why the theory doesn't wrap the whole thing up in a more coherent way where you can talk about symbols, or maybe a better way to state it would be, an LZ system is a system that has the ability to talk about symbols by using previous symbols that you've seen to construct them. But an arithmetic encoder cannot do such a thing. Why do we not have encoders that talk about both of those things theoretically as the same operation? Does that, and I wish I could phrase the question better, but the question in and of itself is about not really understanding how these two things really fundamentally differ and why it feels a little bit underbaked in terms of the way that it's expressed when these two things come together. And since they're always together in implementation, I would have expected maybe a more complete way of looking at it. Does any of that make sense, or are you just like, I have no idea what you're asking?
Well, I'm not sure I know what you're asking, but
okay.
I'll say a few things related to that.
Okay.
So the extra symbols that LZ are adding are totally hacky. It's heuristic. It's like there's no rigorous theory to it. and there's a lot of possibilities there. Different LZ coders add different things.
Okay.
Like traditionally, you add a match, which is an offset in a length.
Yes.
Modern LZ coders add other things there.
Okay.
You know, so there's like single literal matches.
Right.
There's delta literals. There's instead of offsets, you might send rep offsets, things like that.
Yeah, I do remember LZMA had a number of special cases. Like this is a literal match. This is a match that has the same size as a like they had like weird things of like we found this to be efficient, so we've got these
exactly.
crazy.
It's sort of, you think of it as just like a toolbox.
Yes.
Of like these are different ways of sending characters.
Yes.
And you can kind of add whatever you want there.
Yes.
So like Broadly has some new weird things that it's added.
Did you say broadly or broccoli?
Broadly.
Okay.
It's the Google.
I was hoping you said
compression
broccoli
Z.
because I wanted there to be a compressor called
Right.
broccoli, but
And
okay.
WebP lossless has a similar thing where it
Okay.
has like codebook. Like
Okay.
it's trying to send pixels losslessly. It's an
I
LZ,
see.
but it can send pixels as like local palette selections, things like that.
I see.
It just has different modes there. So like you always have a literal as a fallback
Yes.
in case your other options
Don't work.
don't find anything. You
Yeah.
have to be able to send a literal.
Right.
But then you have these other codebook things that are, you know, just ways of grabbing characters. And part of your LZ design is, what do I add in there that is helpful?
Yes.
And to some extent, that's part of your modeling of different data will have different types of things that are helpful there.
Okay.
Like whether your data is binary and has structured repeat patterns or different things like that. So LZ in that sense is an overcomplete alphabet for expressing data.
Right, because everything you send could be expressed many different ways using the LZ
Right.
that you have.
It's like you've made your alphabet too big, essentially, right?
Yes.
Your original bits and bytes are minimal,
Yes.
and then now you're using an alphabet that's like,
Yes.
it's got lots of overlap of lots of these symbols saying the same thing,
Right.
which is a very strange thing in data compression, because doing that is wasteful.
Right, you're
wasting
getting
bits.
bigger to get smaller, which is a
Right.
little counterintuitive, I suppose,
Yes.
right? Yeah.
So, like in traditional coders, in a model coder setup, you don't do that kind of thing because it is wasteful.
Okay.
And in the theoretical analysis, you generally would not do that.
I want this.
It's just something that's practical.
Yeah.
And it turns out that the waste from that is not that bad.
Okay.
There are interesting ways to look at getting rid of that waste that have been done in some LZs, like, for example, if a match that starts with the letter A is available, then you know that the literal A should never be used,
That makes perfect sense.
which means that you could, in your coder, set
Just
the
send
probability
A.
of A to 0,
Okay.
which is saving you some space in your entropy coder.
I see.
So if you look at all your strings that you have, you can get, well, that's not quite precise, but things like that.
Right. No, I get what you're saying, though.
Yeah.
Like you can, instead of allowing the overcomplete alphabet, you can say instead that once I have the ability to express something in one way, I will eliminate the other ways I could have expressed it to reduce the overcompleteness of this
Right,
alphabet. And maybe that's good, maybe that's bad, but I could.
So most practical coders that we use these days are overcomplete, which is kind of interesting to me. Like all the video codecs are way, way overcomplete.
Yeah, in fact, I remember this both from Bink 2 and also from ever looking at like MPEG-4 spec.
Right.
I mean, you can encode the image.
There's
I
like
think
millions of
Fabian
ways.
brought this up even at the HandmadeCon when he was saying if you look at MPEG specs, there's just billions and billions and billions of ways to encode even the same little
Right.
tiny part of an image.
So turns out that being overcomplete and having an encoder that spends a lot of time considering the different choices is an interesting design point.
That seems to be the one that works.
It lets you basically use encoder time to find a good bit stream instead of kind of baking it into the bit stream inherently,
Yes.
which would cost you decoder time.
Got it.
So you have kind of these lots of different ways to encode data, all of which are efficient to decode, and then you're putting the work on the encoder search time to consider all those ways.
That's pretty interesting. So in some sense, you could think of it as we've kind of got, if we imagine there's a uniform constant that's like how much compression plus time there is, we can choose to like move that time around and get more compression by like sort of putting the time into the compressor versus into the decompressor. We can still get the same compression by just moving all the time over to the compressor and leaving the decompressor efficient, even though, you know, in some sense you could have gone the other way, I suppose, maybe. Although I guess I don't know if we know of ways to go the other way, but maybe it's possible.
I'm sure you could.
Sure you could, yeah.
It's something that we haven't really looked at much
at,
because
yeah.
we rarely.
You don't want
we
this,
don't have
but-
that case as often.
Yeah.
It's something I've seen also in terms of just entropy coding, that you have kind of two classic choices that you can do: adaptive entropy coding with a model that changes over time.
Yes.
With arithmetic coding or rants or something like that.
Yes.
Or you can do something like Huffman or TANS, T-A-N-S coding,
Oh, okay.
that uses static models and sends the code links.
Okay. Oh, is TANS technically what it is called if the RANS, and RANS is the incremental version, TANS is the static version?
Well,
Or is that not?
yes, I'm sort of.
Okay.
So TANS stands for table-based ANS.
Okay.
RANS stands for range ANS,
Okay.
which is by analogy to the range arithmetic coder.
Got it.
And that is adaptive. Those are
I see.
both just special cases of ANS in general.
Okay.
So there are adaptive ANS coders that are not rants coders.
I see.
For example.
Okay.
And there's a static version of rants, for example.
Got
so
it.
TANS is not the only static ANS. Those are just two particular ways to do it.
Got it.
So if you are doing static entropy coding, you can spend time in the encoder to find the kind of similar regions of the file and cut it up and
Yes.
send separate statistics for each
one.
segment. So that can take a lot of encoder search time. It's a hard problem.
Right.
But the decoder is still fast because it all
Right,
looks like
doesn't have to
static
do
data
anything.
through decoder.
Yeah.
And that turns out to be very close in size to doing adaptive coding.
I see.
So you get almost a perfect way of taking, in adaptive coding, your encoder and decoder are both expensive.
Right, because the decoder has to be mimicking the adaptive work that
Right.
the encoder was doing, and there's no way to get around that
Right.
additional load.
Yeah, they have to be adapting in lockstep. They have to always
Right.
see the same model.
Right.
So by going to the static with encoder searching,
Yes.
the decoder is now cheap and the encoder is very expensive.
And wait, so you're saying even if, in that case, you're talking about literally I'm sending statistics, so I have to send a little block of 256 bytes or something for each one of these chunks to preload the statistics. I mean, I don't know what exactly it would be, but even given that I had to send that block, it's still close in size to the kind where I didn't have to send anything and I was just doing adaptive.
Correct.
That's pretty
It can
cool.
even be better in some cases.
Because depending on whether the adaptive could get up to the correct adaptation, because the bit stream might not lend itself to that, I guess.
Right.
would be-
I mean, the worst case is when the data is switching back and forth rapidly.
Right.
Like if you have data that's like text and
Yeah.
then an image and then text
Right.
and then an image.
Right.
the static can actually find those transitions pretty easily.
Right. Whereas the adaptive has to adapt on every transition, and if the size of each section isn't long enough, the adaptation may not get there by the time it has to adapt back to the next one, and so on.
It depends. The problem with the the good thing about the static for that case is that the sophistication of your modeling is just in the encoder time.
Right.
Whereas with the adaptive, if you're trying to make it smart enough to realize, like, oh, here's a really sharp transition of statistics, I have to forget all my stuff quickly.
The decoder has to do that same backtracking.
Right, the decoder has to do the
else.
same kind of analysis. So you aren't usually putting that level of sophistication into your adaptive model to be able to detect flush points.
That makes sense. All right, so let me just, to close with, let me just see if I can ask one more time about that, just the little thing, because I'm almost there, but I'm not sure I'm quite there. The answer may be that we don't have any good explanation for these sorts of things. But so still on the concept of the LZ versus the arithmetic side of things. I think originally, early on in the discussion, you said that LZ is understood as a modeling system now. And maybe originally it wasn't thought of that way, or wasn't immediately obvious that that's how it should be looked at, right?
Right.
So can you maybe just give a little bit more insight into that, I guess? Because I think that may also be part of the thing that I was hung up on before. Because, again, it's just a little confusing to think about the way something like arithmetic views symbols, where you're talking about a situation where you actually know what the symbols are, versus something like LZ, where it seems to have this ability to create its own symbols in that sense, right? Meaning it's looking back into the stream of things that it's received so far, and it's saying, what I'm trying to output next is this portion of what I've already seen, right? And again, the part that it's hard for me to wrap my brain around is something like arithmetic thinks about things in terms of symbols, but seems to have no awareness of the fact that that sort of thing could exist. The idea that things I've already sent are, in effect, potentially usable as symbols, right? It doesn't have this notion. It just has a notion of an alphabet that we've predetermined or something like this, right?
Well, arithmetic is just an entropy coder.
Right. And so I'm just kind of curious about that dichotomy a little bit. Like, I guess another way to say it might be, is there really no thing definition of something in between an entropy encoder and a modeling system that is the thing that still has a symbol table, but a set of symbols that it's thinking about, but those symbols are more dynamic? Sorry, this is such a poorly phrased question, but like, okay, maybe let me just say it in the most layman way possible, and you can see if you can make anything of it. There seems to be a world of difference to me between like JPEG, like I'm going to DCT transform this thing into a set of numbers, and then I'm going to think of that as my model. So my model is I take my input set, I DCT it first. That's a step that feels a particular way. That doesn't feel like, in its core, it's thinking about symbols per se. It feels like a totally separate kind of an operation. It's like a modeling transform operation. LZ, while obviously not quite so specific in symbol land as something like an arithmetic or Huffman encoder, it still feels very much like it's thinking of things in terms of symbols in that way. It feels a lot less like a DCT and a lot more like an arithmetic encoder to me when I think about it. Yet it is not that or something. Does that have any more of it? Like, do you see why I think of those things that I'm having trouble placing LZ as a thing in that way? And maybe it's just like, yeah, that's the way it is.
Yeah.
Okay.
So, I mean, there's theoretical compression.
Yeah.
And then there's just algorithms that work. Right?
Okay.
It's just a way of working with the data and expressing things.
Okay.
And so, a couple of points.
All right.
One is that you can always see how a compressor corresponds to a model just by looking at the number of bits that it outputs.
Okay.
So if I run my LZ77 up to a certain point in the file,
Okay.
then I can try adding on each of the next 256 possible characters,
Yes.
give it that character to encode, and see how many bits it outputs for each one.
Okay.
That bit count, if I go 2 to the length on each one,
Okay.
is a probability for each
Yes.
possible following symbol,
Got it.
which is a way of turning any compressor into a model.
I understand.
So you can take the most heuristic, hacky compressor in the world and always figure out what model is this actually corresponding to.
I see. So at any instantaneous point in a bit stream, I can look at the probability that, I can look at the amount of bits that this thing will output for any of the possible things that could come next. And in a sense, I have basically said, okay, that is the probabilistic model of this thing. Now, it is not order 0 in the case of LZ. It depends entirely on all the stuff that came before it, but at any instantaneous point, I can still just look at the order 0 right here, in some sense, and get that at least. Unwinding the rest of it may be impossible because it's some crazy Turing machine who knows what what it's doing, but just instantaneously I can look at it that way.
Right.
Yeah.
That's the probability of what is the next character given all the previous characters.
Yes.
Right. So every compressor is a model in that sense, and LZ is
Got
a
it.
way of getting
Getting
to
that.
those output lengths.
Okay. That makes a lot of sense. Okay.
The other thing is that, you can think of the extra symbols as ways of kind of getting to the arithmetic coder. I don't know if I can say this clearly, but so like, say you have a model that is just predicting its most likely guess for the next symbol.
Okay.
Like it makes one guess, and then if it's right, it outputs a 0 bit.
Okay.
If it's wrong, it outputs a 1 bit, and
Okay.
then what the character actually was.
Got it.
So it writes 9 bits.
Got it.
So what we've actually done there is added another symbol.
Okay.
So we have our literals.
We've added the yes/no bit, or,
Well,
or the accurate inaccurate
You've
bit.
got we're outputting 0 for right and 1, and then 8 more bits.
Right.
If we're wrong, let's say A, B, C, D, whatever.
Yep.
So this is 9 bits total.
Okay.
You can think of this as a combined alphabet. This is the symbols 0 to 255 that are our literals. This is symbol 256.
Okay.
And I'm giving this a 1-bit code, and these all get a 9-bit code.
Got it.
So this is my like super simple LZ.
Okay.
And I've added a symbol to my alphabet to specify, hey, my guess is right.
Okay.
So all LZ is doing more of this.
Okay.
Right.
A more complicated set of possible.
Adding more
Right.
special symbols
Okay.
and giving them special codes.
Okay.
And that's what heuristic compressors generally are doing.
And the reason why why an LZ compressor itself isn't concerned about how to encode things in the correct number of bits is because, fundamentally speaking, at least so far, nobody has figured out any particular reason why the way you would do that would differ from just arithmetically encoding the actual things that the LZ is doing. Right? Because in some sense you could think of an arithmetic encoder is a thing that's trying to figure out, well, not trying to figure out, it's a machine for correctly outputting the minimal number of bits to encode this set of symbols that it's trying to input, right? The LZ encoder is not concerned with doing that. It's not concerned with trying to get the optimal number of bits. It's just trying to produce a series of match versus not match. And it wants to produce the minimal number of bits with that in mind, but it's not trying to get down to fractional or anything like that. So you might say the reason why it's not concerned with that is because the way that we have chosen to try to approach that is just, it seems like bolting an arithmetic encoder onto the back of it is as efficient as trying to figure out a way to integrate that directly into the LZ scheme. Because like in a fanciful world, right, and again from layman's perspective, you could imagine an LZ encoder that itself was working on fractional bits. I don't know what that exactly means, but like the concept that I have to copy out of a 8-bit at a time bit stream doesn't really have to happen. Like an LZ encoder could, a similar thing to an LZ encoder could maybe be done imagining working on an infinite fraction, grabbing parts of the infinite fraction out, which means that now it's fractional bits in terms of the input. I'm making this up, but you see what I mean, right?
Yeah. I mean, so we usually work on bytes just out of practicality.
Right.
There's no inherent theoretical reason why we have to.
Right.
And like the careful people in the literature will do their arithmetic coding in terms of base B.
Right, right.
Is arbitrary.
Arbitrary, yeah.
But it, you know, as a
Yeah.
programmer reading it, you
Right.
always think that's 2 or
Right,
2 or
right,
6,
right, right.
Like I'm not doing
Yeah.
ternary
Right.
like arithmetic.
Okay.
So that's all possible.
Yeah.
There are more general things. So let me, in terms of LZ, you could, at each step of your coding, look at, like in the LZ aspect of it,
Yes.
before we get to the entropy coding,
Yes.
we could look at like, hey, some of my heuristic code words are not even possible in this location where I am.
Yes.
So let me exclude them from my code words. Like maybe early on in the file, you don't have much dictionary.
Right.
So there's lots of things that aren't possible, like large
Right.
offsets aren't possible.
Right.
Maybe you haven't even seen all the literals yet.
Yes.
So you know, you can't possibly match them and things
Yes.
like that. So you could be doing more at that step in the LZ.
Right.
And people have tried it. There's lots of variants along there. There's things like LZFG, LZPP. More recently, there's Ken and Conrad's work on tree, which is kind of an
Okay.
interesting thing in this direction.
Okay.
For the most part, spending CPU work there is not a good trade-off.
Okay.
That they're just better places to put
put
that
it.
CPU work.
Okay.
So, I mean, to some extent, the answer there is compression is always an issue of design of where are you putting your CPU work.
Got it.
And, you know, there's always options. You know, there's no shortage of ways we can increase the amount of CPU work. I can always do some more modeling.
Yeah.
There's always, you know, so one of the, there's like all the redundancies and the overcompleteness of the LZ you could model and eliminate if you wanted to spend the CPU work on it.
Yes.
But it takes work, right?
Yes.
There's correlations all over the place in LZ that we know are there and we could model and take out.
Okay.
Like the previous character, for example, predicts a lot about what the current sequence, what the current symbol is going to be, or whether it's a special word or
Okay.
things like that. And the previous occurrence of the same match, like once I send my offset, I know I can go back to that spot in the file because I've sent the offsets. The decoder
Right.
could do the same thing.
Right.
I can look around that offset at the data there. It's probably very similar to where I am now.
Okay.
So I could be using that information
But I'm not.
to predict things about my local neighborhood.
I see.
But I'm not. Other than, you know, obviously you're copying the match, but even outside of the match region, there will be similarity.
Stuff that you might want to know. Yeah.
Yeah. So there's lots of opportunities, and it's just like, what can you express well that is efficient enough?
Got it.
Because the speeds we want to run at now, we don't have a lot of time
to do anything.
much of anything.
Got it.
You know,
in the decoder. In the encoder, you can afford to be slow, I suppose, to a certain extent.
That's the design point that we work at RAD usually is slower encoders, faster decoders. And we only get like 1 to 10 clocks per symbol in the decoder.
Gotcha.
So you can't do
very much
in there, right?
All right.
So in addition to that, so like if you look at LZ, there's lots of points where you can see that we're wasting bits.
Okay.
And it's just a question of how do we get them without spending too much time. There's also of course like another level of things you're missing that LZ don't model well.
Okay.
So there's a whole other issue of like what other compression is available in this file.
Right.
That I'm never going to get with LZ.
Right, like the preconditioning sorts of stuff, like differencing from symbols or things like this that people have added to LZ, I guess. I think LZMA has some things like this, of this nature, right, where it'll delta symbols from each other or things like that before encoding or stuff like this, which is not technically in the LZ scheme, I think.
Right.
Yeah. All right, well, I think that's everything. Thank you so much for explaining all of that. That's been very, very helpful, and hopefully we've got. It looks like everything went well enough. People seem to have been able to have heard us even though we have our crappy little webcam.
Uh-huh.
So thank you so much, Charles. That's been awesome. I will post this along with the HandmadeCon one so everyone can get the complete package. And I guess also at some point people probably should take a look at your blog. There's a lot of compression stuff on there. Should I include the URL with this video potentially, or do you just like no, the blog is secret, don't come to it?
Yeah, we can include the URL.
All right, I'll put it on the bottom. So thanks very much for being here. I will go ahead and I will close down the stream.